Hello all, in this lesson we are going to be studying enthalpy and entropy, and we'll also use a little bit of information from table I, so have your reference table ready. All right, folks, so I need you to copy down this particular homework. Of course, don't do it, just copy it down, and here's your aim for today. What are enthalpy and entropy, and how is table I used? And then follow it up with these do-not questions, which we will do in class tomorrow. All right, enthalpy. Enthalpy comes from the Greek root for heat, or thalp. So the thalp is giving us heat, and enthalpy would be the heat within. So that's why you see that here, and we can also symbolize that with delta H. So enthalpy, delta H, heat within, all means the same thing. Now, most chemical reactions are exothermic because the potential energy of the products is lower than that of the reactants. Therefore, the particles in a system are much more likely to collide with enough energy to carry out the forward reaction than the reverse reaction. So this drive towards lower energy is called a drive toward lower enthalpy. You can use table I to help show this. Everybody take a look at table I now. So I know it's going to be a little bit small, but I inserted one here for our reference. Let's answer some of these questions, and we'll also get a chance to talk about table I and delta H in the process. All right, first up, when glucose reacts with oxygen gas, it results in products that have blank enthalpy. So let's look for the equation that has glucose reacting with oxygen gas. Glucose is C6H12O6, and here's my oxygen gas. Then it's producing the 6CO2 and the 6H2O, and the delta H is negative 2804. So if you have negative 2804 delta H, or just a negative at all, that means that the reaction was exothermic. And in an exothermic reaction, the products have less energy than the reactants, but here we're using the word enthalpy, which is the same idea. Enthalpy is heat, and heat is energy. Next up, when aluminum reacts with oxygen gas, a blank type of reaction occurs. So let's find the aluminum and oxygen reaction. It's right here. So here's aluminum reacting with oxygen, and it's negative 3351. So that means we have an exothermic reaction going on. Next up, the potential energy of the product of the dissolution of ammonium chloride. So let's look for ammonium chloride dissolving in water. So here's ammonium chloride in the presence of water, and it's producing ammonium ions and chloride ions. This is a positive 14.78, which means that it's an endothermic reaction. And endothermic reactions are ones where the products end up having more potential energy than the reactants. So let's see if that helps us. The potential energy of the products are more than that of the reactant. Okay, so the formation of bonds, according to table I, generally results in products with blank enthalpy. So if you look at a couple of examples where bonds are being formed, like here, we have negative delta H. Additionally here, we have negative delta H. And let's choose another one here. That's negative delta H. So it looks like generally when bonds are formed, you have a negative delta H, and that the products have a lower amount of heat or enthalpy. And the breaking of bonds, I can find a couple of examples, but like here, the breaking of bonds here seems positive, and additionally here, the breaking of bonds seems positive. So the breaking of bonds is typically an endothermic reaction, which means that the products have higher enthalpy. And we also have this idea of entropy. Now, entropy is the tendency in nature to move towards a state of chaos or randomness or disorder. And if you were looking at these two bedrooms down here, this one would have very low entropy and this one would have very high entropy. There's lots of chaos, lots of disorder. When you look at a cool chemical diagram like this, the one that looks more organized is this guy. He's more organized because he's drawn up into a compound. And these guys are less organized because they're floating freely and unbonded. So you guys definitely need to know that in a chemical change, the compound itself, like this guy, has more order than these free elements. So I'll write in more order and less order. So breaking bonds drives reactions towards lower order or higher entropy. But there's also the changes that happen when we just go through a physical, like a phase change. Like solids will tend to change to liquids, and liquids tend to change to gases, and gases would have the most chaos. So that means that phase changes drive towards lower order or higher entropy. All right, let's do a learning check. Let's label the checkerboard arrangements with their respective levels of entropy, indicating decreasing or increasing entropy between the boards. So those are my answers. The highest entropy is going to be there on that right-hand board, and the lowest entropy would be over on the left-hand board, increasing left to right. Let's also label each method of checker storage as high or low entropy. The lowest entropy is going to be where you can find the most order, so I would suggest that that one would be the lowest entropy. All right, let's do this pair up tomorrow, but I do need you to copy down the questions now before class begins. Same thing for this summary. Make sure you have the questions ready before class, and we'll do them in class tomorrow. Thank you guys for watching. I hope you learned a lot about entropy and enthalpy.